This section is section 28.5. It's the fifth section under magnetic field sources that we have been discussing. And here we're going to talk about diamagnetic substances. This is very similar to the dielectric substances that we had with the electric fields. Now you'll recall that if we had an electric field, let's go back to that situation, we might have a capacitor, and we've charged this side positive and we've charged this side negative, and therefore there's an electric field, always goes away from the positive toward the negative, and there's an electric field that exists in this space. Now if we were to put some kind of substance here, then that substance can do one of two different kinds of things. It can, first of all, if there are dipoles in this material, like for example water, which are tiny poles that have a positive and a negative center of electricity that are separated, these dipoles can rotate because there's a torque on them. And they will rotate in such a way, actually in this case this way, this way, so that the positive would become more oriented toward the negative and the negative would become more in this direction. And the overall effect is such dipoles reduce the field that exists here. Okay, so that's the first effect. The second effect is one where there are no dipoles, but you can induce dipoles in the material, so you can basically say, okay, here's the substance that's in the middle of this capacitor, and it feels this electric field going through here, so this electric field will push the positive charges to this end and the negative charges to this end, and therefore it will result in a reduction of the field even though there are no dipoles there because of the motion of the charge. And so there are two effects that obtain when we're dealing with electric dipoles, and we talked about that associated with the susceptibility of the various materials when we talked about the electric field. We're now going to talk about the same kind of situation when we get to magnetism. And if we have, for example, a magnetic field, B, and it's an empty space, then we have one kind of situation. But if there's some kind of substance here that's placed in this magnetic field, it will alter the magnetic field so that the total magnetic field in here is the B naught that we originally had, plus a B due to the magnetization that exists within the substance. So we could write B total is equal to B naught, the original field before the material was placed there, plus Bm, which is the magnetic field due to the material. Now that can be written as B naught plus mu naught times m, where m is here defined as the magnetic moment per unit volume. It's called also the magnetization vector. M is the magnetization vector. Likewise, I can pull a mu naught out of this B naught and obtain something that we call H, and write this as mu naught times H plus M for the total magnetic field B. And of course this is due to the natural effect that we have. This is due to the magnetization. Now for different types of substances, of course this M is going to be dependent upon how strong the H is. Now what is that relationship? It turns out that for two types of substances, paramagnetic and diamagnetic substances, the relationship is linear. So we can write where the magnetization is equal to a number called chi times H. And of course different substances have different chi. Chi is called the magnetic susceptibility. Magnetic susceptibility, chi. Then we can write mu with the material is equal to mu naught times 1 plus chi. And then this comes from the fact that if we put chi times H here, then this would become mu naught times H times 1 plus chi, And then we can replace this 1 plus chi mu naught. This is equal to this. And then that will equal to H times, as you can see, mu naught times 1 plus chi mu m. Very similar to what we had originally with mu naught times H is now mu m times H, where mu m is the permittivity of the system. Now, to look at our different systems, if mu m is greater than mu naught, this substance is called paramagnetic. If mu m is less than mu naught, then it's called diamagnetic. Then there's a third condition that's called ferromagnet. In these two situations, we have a linear relationship. But with the ferromagnetic, we do not have a linear relationship. In that case, mu m is very, very much greater than mu naught. Well, let's look at some examples of these different types of substances. Paramagnetic substances. Examples of those would be aluminum, calcium, chromium, lithium, magnesium, niobium, oxygen, platinum, and tungsten. For just one example, we might write for aluminum, chi there for aluminum is 2.3 times e to the minus fifth. For something like lithium, it again is 2.1 times e to the minus fifth. For magnesium, it's 1.2 e to the minus fifth. So this number varies, but this is pretty much standard, except oxygen, it's smaller, and for platinum, it's greater, it's e to the minus fourth. So the range is about e to the minus fourth to e to the minus sixth in looking at our magnetic susceptibility of various substances. Now, this is paramagnetic. We can also have diamagnetic substances, and our diamagnetic substances are bismuth, copper, diamond, gold, lead, mercury, nitrogen, silver, and silicon. These are, of course, negative, and chi here is equal to something like minus some number, like with gold 3.6 e to the minus fifth. Again, e to the minus fifth, the opposite sign obtains because it's in the opposite direction, and it's something like 3.6, 5.0 for nitrogen, silver's 2.6, but it's going to range around e to the minus 5, except for nitrogen, which is e to the minus 9 at standard temperatures and pressures. Then for iron, for ferromagnetic substances, we have just a few things that give tremendous effects for magnetization, and they actually have a memory called the hysteresis curve, and they can remember how they've been magnetized and demagnetized. But that takes us a little bit further from our examples that we wanted to cover here. This finishes our discussion of diamagnetic substances.